Hey everybody, welcome back. This is our third and final lesson for the week in acid-base chemistry. This one is really short and sweet. So you guys, day one learned how to write acids and bases using the Arrhenius modified definition. Yesterday you guys did pH and pOH calculations and learned about those special sig-dig rules. And today I'm going to introduce you guys to Kw, which is a way to convert between hydronium and hydroxide concentrations. So the formula for Kw is written here. It's concentration of hydronium times concentration of hydroxide, and it's 1.00 times 10 to the negative 14. So it's a mathematical constant. It always holds true for any aqueous solution, which is kind of interesting. So we're going to go back to our simulation, and I'm going to make these guys equal at 7, as close as I can get. Okay, so there we are. We'll call those equal at 7. Come on, let's go. So when they are at pH of 7, concentration of hydronium equals concentration hydroxide. And if I multiply those together, 1 times 10 to the negative 7 and 1 times 10 to the negative 7, I get 1 times 10 to the negative 14, which is where this value comes from. So if concentration of hydronium is 1 times 10 to the negative 7, and hydroxide is 1 times 10 to the negative 7, we always get 1 times 10 to the negative 14. If one goes up, the other has to go down. So one goes up, the other goes down, but their product is still 1 times 10 to the negative 14. So I'm going to stop right there. So I've got 1 times 10 to the minus 2 and 9.9 times 10 to the minus 12. If I put those into my calculator, 1 times 10 to the minus 2, 1 second exponent negative 2 times 9.9 to the negative 12, we get 1 times 10 to the minus 14. So it doesn't matter what these two numbers are, their product is always 1 times 10 to the minus 14. If you want, you can try that with these two. 10 times 10 to the negative 3, 1 times 10 to the negative 12, multiply them together, and you get that mathematical constant. So this is really helpful because it allows us to convert one concentration to another. So for example, if we have a hydronium ion concentration of 8.1 times 10 to the negative 11 moles per liter, we can determine the hydroxide concentration. So how would we do that? Well, we'll use our Kw, which is 1 times 10 to the minus 14 equals concentration of hydronium times concentration of hydroxide, and we want to solve for hydroxide. So we'll rearrange. To rearrange it, we're just going to divide both sides by H3O plus so that it cancels out there. And there's our new formula. So 1 times 10 to the minus 14 divided by concentration hydronium equals concentration hydroxide. Now I just have to plug it in. So 1.00 times 10 to the minus 14 divided by 8.1 times 10 to the negative 11, and put it in my calculator. The answer is, I love this number. The answer, believe it or not, is 1.23456 times 10 to the negative 4. How cool is that? Okay, sig digs, we've got, these are normal numbers, not pH, so 3 and 2. So my final answer is 2 sig digs. 1.2 times 10 to the negative 4 moles per liter, and that is the concentration of hydroxide. Now I want to do a second one with you. You don't have this one in your notes, but you can write it down. So this time we have a concentration of hydroxide that is equal to 3.5 times 10 to the negative 6. What is the concentration of hydronium? So to figure that out, we'll use Kw. Concentration of hydronium is Kw over concentration of hydroxide. 1.00 times 10 to the minus 14 divided by 3.5 times 10 to the negative 6. And that one works out to be 2.857 times 10 to the negative 9 moles per liter. And sig digs, these are normal numbers, not pH. 2 sig digs, 3 sig digs, so my final answer is 2. 2.9 times 10 to the negative 9 moles per liter is concentration hydronium. All right, so you can see how Kw is useful for converting hydroxide to hydronium, hydronium to hydroxide. This little diagram shows you how hydronium and hydroxide are inversely proportional. As hydronium decreases, hydroxide increases. And this line in the middle represents their product, which is always 1 times 10 to the minus 14. So if I take this one and multiply them together, I get 1 times 10 to the minus 14. If I take, what's another example? If this was 10 to the negative 12, this would be 10 to the negative 2, and their product would be right here, 10 to the negative 14. As one goes up, the other goes down, inversely proportional. Okay, now I don't know why this one's in your notes, but we're going to kill it. We don't need to do that one. So we have 2 problems to do. They're both doozies, and then that's it for today, and then you have an assignment that'll take a little bit of a while to work on. So let's take a look at these 2 problems. What is the pH of a solution made by dissolving 4 grams of hydrochloric acid in 500 milliliters of water or aqueous solution? Okay, so first thing I want to do is figure out my concentration of HCl. Let's start there. Concentration, and we want amount concentration in moles per liter. So I have 4 grams, and I have half a liter. So I want moles per liter, and I have grams per liter. Where do I get moles from? Molar mass of HCl, which is 36, capital M. Molar mass of HCl is 36.46 grams per mole. 3545, 1.01, yep. Okay, so I want moles per liter, so I'm going to flip that. Moles over 36.46 grams. Okay, now we just need to cancel out our grams right there. 4 grams, they're gone. So now I have moles, but I want moles per liter, so I'll put this liters on the bottom. So now my units are moles per liter. Multiply all of that together. Make sure I got all that right, and we get 0.219 moles per liter. That's our concentration of hydrochloric acid. Now the question is asking for pH, so I need to get the concentration of hydronium. We know from modified Arrhenius that hydrochloric acid in water will react with water to make hydronium and is Cl minus. So if I have, and let's go sig digs, 2 sig digs, 0.22 molar HCl, I can use stoich, 1 hydronium for every 1 HCl, so it's going to be the same. I'll get 0.22 molar hydronium. That makes sense when you look at it. 1 HCl turns into 1 hydronium. So concentration of hydronium is 0.22 molar. The last thing I need to do is pH. So pH is negative log of concentration of hydronium. So that's going to be negative log of 0.22. And I would carry all my digits through because this is an intermediate calculation. Carrying all the digits through, we get 0.66. And that's 2 sig digs. 2 decimal places on our pH. There was our raw digits, our unrounded digits on the hydronium, and there's our final pH, 0.66. So that's pretty acidic. It's getting close to a pH of 0. So as you can see, there's a lot of steps in that question. You have to be an organized smarty pants to get your way through that one. So this is where we're headed. We're going to do one more of these, and then you guys get your assignment to practice these. Okay, so this time we're doing the exact same thing. We're taking 4 grams, but this time it's a base, sodium hydroxide, and dissolving it in half a liter. And we're looking for the pH. So let's start off with concentration of NaOH. Same pattern. Molar mass of NaOH is 40 grams per mole. Okay, so let's start there. We want the moles per liter. So moles over 40 grams. I have to get rid of grams. 4.0 grams on top. Grams are gone. Liters on the bottom. And we get moles per liter. Okay, plug that into your calculator. And we get... what do we get? 0.20 moles per liter. 2 sig digs because of that 4 grams, 2 sig digs. Okay, so there's our concentration of NaOH. Now remember, ionic hydroxides are different as a base. All they do is dissociate. So NaOH dissociates in water into Na plus and 1 OH minus. So if we have the concentration of NaOH, capital M, moles per liter of NaOH, we can use stoic. 1 hydroxide for every 1 NaOH. Here's my puppy going bonkers. And it's the same, 0.20 molar. Ooh, that turned out messy. Let's try that again. 0.20 molar. Okay, so we've got the concentration of hydroxide. So here's the tricky part. How do we get the pH? Well, we can get pOH first. pOH is negative log of the concentration of hydroxide. Negative log of 0.20. And that is 0.6989. And it's going to be 2 decimal places, so 0.70 for sig digs. Okay, so that's pOH, but the question asks us for pH. This is why base problems are hard. You have that extra step. So pH is going to be 14 minus pOH. 14 minus 0.70, which is 13.30. 2 decimal places for the 2 decimal places on our pH. Okay, phew, you can see why these questions take a little bit of work. That's called a multi-step problem. Lots going on there. So you may have to watch this video a second time to understand those patterns so that you can successfully navigate through the assignment. And we'll talk about the assignment in a minute. These are all the formulas you need to know. They're not in your data sheet. You need to remember them. I'm going to show you a little trick to help you remember these. It's called the conversion square, I guess is the best thing you could call it. So here's how it goes. And you can write this on a quiz or a test. Everything's open notebook, so it doesn't really matter. But okay, if I have pH and I want to calculate concentration hydronium, what's the formula to do it? To get from pH to hydronium, if I have pH and I want to calculate hydronium, it's 10 to the negative pH. 10 to the negative pH. Okay, but if I want to go the other way, if I have hydronium and I want to get pH, then it's negative log of hydronium, concentration hydronium. Okay, that's one side of the formula. Now I'm going to go pOH and concentration hydroxide. So these formulas are the same. pOH to hydroxide, I go 10 to the negative pOH. If I want to convert hydroxide to pOH, I go negative log concentration hydroxide. So by remembering one side, you can remember the other. Now here's the interesting part. If I want to convert concentration hydronium to hydroxide, I can use Kw. If I want to convert concentration hydroxide to hydronium, Kw. And if I want to take pOH and convert it into pOH, I go 14 minus pH. And if I want to go this way, pOH into pH, it's 14 minus pOH. So you can see we've made a square. And this summarizes all of the formulas. Now, one of the useful things about this is I call them one-step and two-step problems. If I want to get from pH to pOH, that's one step. If I want to get from pH to hydronium, that's one step. What if I want to get to from pH over to hydroxide? That's a two-step problem. I can go pH to pOH and then to hydroxide, or I can go pH to hydronium and then to hydroxide. So you can travel in either direction around the square, doesn't matter, and it's just a useful way to keep track of all of your conversions. So if you find that useful, you can write that out on a sheet of paper and keep it nearby, and then you can use it for all of your calculations, or you can remember all of these. Your choice. Okay, we're done. This is a tricky page. I'm going to put the answers on Google Classroom for you to check as you work through them. These are challenging, and these are the types of questions you're going to see on your quiz tomorrow to wrap up this week's work. And I don't have this one because I usually hand that out in class, but there's these as well. Okay, so textbook page 244, 3 to 6, and study guide page 216 for me, page 220 out of Kelly's. Okay, make sure you get a whole bunch of that done as much as possible so that you're ready for your quiz next class. All right, take care, everybody, and we'll see you tomorrow.